Hello and welcome to Worksheet 2. We're gonna go over Worksheet 2 for a couple minutes here. Shocker, you're gonna need a periodic table. Of course, you're gonna need your purple packet. And when this is all done, you need to show your work to the sub. They will be writing down a 10 out of 10 for people who've shown it all. And for those of you who've shown a whole lot less, you'll get less. The first things first, though, these first 5 questions are a whole lot like what we just did on the quiz to start off with. So you have the, is it soluble or insoluble? Is it soluble or insoluble? You're looking at the rules and trying to figure it out. I think this is rule number 1 because ammonium is always soluble. And I think this is rule number 3 because chlorides are pretty darn soluble. I think this is rule number 1 because potassium is a group 1 element. This one here, magnesium sulfide, I feel like that's rule 7. I don't have a sheet in front of me, so don't, you have to look carefully, and I know that either 6 or 7 says that sulfides are insoluble, and then it lists magnesium as being an exception. I just can't remember which rule it is, so don't quote me on that one. And then number 5 really throws people off because it says dichromate. Dichromate isn't anywhere, but ammonium is specifically called out in the first rule, and it says ammonium is always soluble. So for some reason, every single question here on worksheet 2 is soluble, 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 which is a fun thing to say. Not really all that fun. But there's a second part to this question. And it's written up here, and it says, if it is soluble, write out the dissociation equation in the space provided. And we didn't do a terribly good job of doing that in the notes. That was right at the end of the notes. And so I'm going to review that and then kind of talk through the answers here. So up in red, I have the basic concept of a dissociation equation, and then I'm going to do some fancy drawing also to explain it. So I have A2B, and that's just whatever compound, like salt or calcium chloride or ammonium hydroxide. It's whatever the formula for the compound is, and I'm just pretending it's A2B. All right, that's the formula for my fake compound. And this compound is a solid, and it gets dropped into water. And it's not reacting with water, it's dissolving in water. And I know it's dissolving in the water because I check the solubility rules and I find that my compound is soluble. And so this compound here is actually K, ew, that was horrible handwriting, is actually K2, so that would kind of be like our A2, and the carbonate is the B, it's the other half. So this compound is soluble in water according to the solubility rules. Well, that means it dissolves, and dissolving really means something that we don't quite grasp often. Dissolving means that it breaks apart into ions, and that's what I have represented in this equation here, is that the A ions and the B ions are now separated and surrounded by water, and you can tell they're surrounded by water because it now says AQ, and AQ stands for the word aqueous, and aqueous means floating in water, dissolved in water. So we're supposed to write dissociation equations for every single one of the soluble compounds. That happens to be every one of them this time. Sorry about that. That's just totally by accident. When we get to the test, there will be a couple of these where you have to write out the dissociation equation. And it's pretty obvious when people don't know what a dissociation equation is because they come up to me in the middle of the test and they say, what's a dissociation equation again? So, take this moment, write yourself some notes so that you know what a dissociation equation is. It's when a solid dissolves in water and breaks apart into its ions. So our first compound is ammonium hydroxide, and it is going into water. So just like before, I wrote the compound as a solid, and now it's going into water. See, the water's right there on the arrow. If it is soluble, this compound will break apart into its ions. Well, its ions are spelled out right in the name. its ions are ammonium and hydroxide. So you have to split it into its two ions. So guess what I have on the right side? I have ammonium and then hydroxide. I split them apart as ions and show that they are now dissolved in water. Hey, wait a minute. Up here you have a 2, but down here I don't see a 2 in front. Well, so this formula had 2 A's. This one only has NH4 one time. So you're only going to see NH4 one time. And it has OH one time. So you only see OH one time. So you do have to look at the formula that you created to figure out how to break it apart. Let's go to number 2. So the formula for calcium chloride is CaCl2. And again, I didn't kind of review that part, but we did this in class the other day. Let me just go. I go to the periodic table. I find calcium. Calcium has a +2 charge. I go to the periodic table. I find chlorine. Chlorine has a -1 charge. And since those charges are not equal, I then swap the values down here. So for every 1 calcium, there need to be 2 chlorines. Okay, so that's my review of figuring out ionic compound formulas. If you need more review, go find my video on nomenclature and ionic compounds, because that's a thing you can do to get that under control. So anyway, this compound is CaCl2. Notice that the 2 is on the chlorine this time. It's on the second thing, it's not on the first thing. So when we break this up, boom, the 2 is in front of the chlorine, not on the Ca. Okay, gonna keep kind of going. It's the same pattern. Bam, K2CO3, water, 2 Ks, and a CO3. I got a follow-up question, Mr. Murphy. Okay, I hear you. What about this 3? Remember, that 3 is part of the polyatomic ion. It is a thing we've been writing with carbonate again and again and again, and that 3 doesn't come off very easily. The polyatomic ions don't break apart further in water. They'll split from whatever they're paired with. In this case, it's paired with potassium, but they're not going to break down themselves even further. So the CO3 with a -2 charge is what's dissolved in the water, away from the Ks. Magnesium sulfide is dissolved in water. It is one of those exceptions. And then ammonium dichromate. I can't remember dichromate. Oh my gosh, what am I going to do? I'm going to look at the back of the periodic table and find this weird polyatomic ion, Cr2O7. And then ammonium is right there. And so then I have 2 ammoniums and the dichromate. The only problem we really ran into with questions 1 through 5 is we didn't have the counter example. All of these were soluble and they were all dissolving, and I don't have a counter example in this worksheet. So let's throw a counter example just on your paper right here. What about insoluble? Yeah, maybe you didn't see that there. It's hiding in black. Well, if it's insoluble, that means it doesn't dissolve in water. So we'd have a similar format. We would have our this one's insoluble. Lead sulfide is insoluble if you look at the rules. Oh, there it is. And therefore nothing happens. So I wrote lead sulfide becomes lead sulfide. It's solid before, it's solid after. Or you could just write nothing happens. Yeah, those are the easy ones, aren't they, if they're insoluble. Okay, now let's start talking about predicting the products. So we have very different and distinct types of reactions. As we get into the next couple of questions, we're going to see a whole lot of problems where the right side is blank. And so as we look at those right side blank questions, we need to realize they're going to fall into one of these 3 categories. They're either going to be a double replacement, they're going to be a single replacement, or they're going to be some sort of combustion reaction. Man, I can't spell combustion for some reason. At least they didn't write the U before the B, right? Who would write the U before the B? Combustion. So we have a double replacement, a single replacement, and combustion. But we don't actually get to see this part. So we need to know the left side pattern well enough to then predict the right side pattern. So let's talk about these left side patterns. With the double replacement, we have a compound and a compound. Got that? It's two compounds and the pieces are different. Might be potassium, carbonate, ammonium, hydroxide. That's four different pieces. Like, it could be ammonium, hydroxide, potassium, carbonate. So A and B, C and D. And once we've identified that we've got two compounds, we know that the pieces are going to switch around. That's how you identify a double replacement. Two compounds. Single replacement. You have the one compound, and then, and this is why it's called this, you have the single element. Single element. So you have the single element, and that element is not oxygen, by the way. Spoiler alert, that's going to be in a second. But you have that single element, and that single element might be able to replace one of the others. So it might be able to take the place of B or C. And the key with these questions is we have to check the activity series. And when we check the activity series, we're going to look and see, is A higher? Alright? So if A is higher, when A is higher than B or C on their list, it takes the place of that element. So like potassium is pretty high on the list, and it could replace copper. So if potassium was A and copper was B, it would replace B, and then the potassium would be bonded to whatever the heck that other element was. What if A is lower? If A is lower, then nothing happens. So if A is at the bottom of the list, that's gold and silver and platinum. Those are the metals that are at the bottom of the metals list because they're so unreactive that we wear them. When A is at the bottom of the list, nothing happens. So you have no reaction. And that does occur on the test. It does occur on this worksheet. We'll see a couple of examples of that. And then the third one, where we actually have to predict the products, is a combustion reaction. Combustion reactions follow a very consistent left side pattern. Let's just remove the right side one more time. So the left side is carbon and hydrogen reacting with oxygen. Carbon and hydrogen reacting with oxygen. Alright? And so the products are going to be CO something and H2O. CO some value down here for oxygen and H2O. And this value down here totally depends on how the oxygen is described. If there's a lot of oxygen, then you're going to burn really well, and you're going to make carbon dioxide. That is to say that if there's a lot of oxygen, this value here is a 2. What if there's not much oxygen? Well, if there's not much oxygen, then this value here is a 1. Now, we have a very simple way of telling you if there's a lot or very little oxygen. Let's go look at a couple of examples. I'm going to go to a question. Let's go to question 22. So, question 22, it says we have carbon and hydrogen reacting with, and my plus sign is covered up by all my amazing boxes, reacting with oxygen. So this fits the CH plus O2. And then it says that the oxygen is limited. There's not a lot of oxygen. So they're telling us about the reaction by describing the oxygen right there with a word that is limited. And then in other times, where's my other? There it is. Number 13, it says you have carbon and hydrogen reacting with oxygen, and the amount of oxygen is excessive. It's just a lot of oxygen. And so these two types of reactions get treated differently. So if it was an excess amount, then it would be a 2 right there for the question mark. If it was a limited amount of oxygen, it would be a 1. Alright, so those are the three types of reactions that you actually have to predict the products. There are still decomposition and synthesis reactions. And with decomposition and synthesis, you're getting that page just like you had on the quiz. The products are already going to be predicted. You just kind of have to figure out what type of reaction you're looking at. So those are treated a lot easier than these three. So the first step in this worksheet is to go through and identify the different categories. You might kind of come back to this page a couple times. Is double replacement, single replacement, combustion, decomposition, or synthesis. The basic format for decomposition is that the compound is breaking apart. Wow, look at this live typing. That's great. And then the basic formula for synthesis is that you have some pieces and they're coming together. And essentially decomposition is always one thing breaking apart, and synthesis is always a couple of things making one thing. So they're opposites of each other. So they're usually very easy to identify that it's decomposition or synthesis, and then the specific type, you have to look at that sheet a whole lot. But let's go find a couple decompositions. I think the decompositions are easy to find. So let's see, this is too many things, not a this is only one thing. And look, it's breaking apart. It must be a decomposition. So I look at the sheet, and it looks like decomposition number 6. And again, that sheet is on page 144 for you all. Page 144, so you flip. Oh, look, at decomposition number 6, it says that there's electricity being used to break the compound apart. So this is definitely decomposition number 6. And then I balanced the reaction with these amazing 2's. And I threw some states of matter in there also. These spaces were blank. And how did I figure out the states of matter? Well, I thought about it for a second. Hydrogen and oxygen are both gases, so I put gas on there. Don't know that those are gases? There's a periodic table in the front of the room. The letters on that periodic table are color-coded. Maybe you haven't noticed that. But the red letters, like oxygen, and hydrogen, and chlorine, and fluorine, and bromine, not bromine, that's not bromine. The red letters are gases, all right? The blue letters are liquids. Now you're straining at the periodic table, and people are looking at you funny because you don't see blue up there. There's only 2 blues. Bromine is one of the blues, and Hg, mercury, is the other blue. You'll notice that most of the letters up there are black, and black stands for solids, which makes sense if you start looking at some of the elements that are black, like lead and iron and aluminum, and you go, oh, right, okay, they make sense, that's a solid. Okay, so we've done all of one question. Let's go find another decomposition. No more decompositions on this page. This is 2 pieces, 2 pieces, 2 pieces, 2 pieces. Decompositions are only ever one piece breaking apart. So go to the next page. Number 12, one piece breaking apart. Definitely a decomposition. Looks like decomposition number 1. Looks like decomposition number 1 because it's got CO3, and decomposition number 1 talks about carbonate. This one state of matter, I wouldn't ask you for that one, but I think you know the state of matter for carbon dioxide. So I would ask you to put the state of matter for carbon dioxide into there, and it's a gas. Spoiler alert, it's a gas. Number 16 is also a decomposition. There's actually a typo in there. It doesn't work the way it's written. Sorry about that. Looks like decomposition number 2. It is one compound breaking apart with heat, and the compound has hydroxide, which is exactly what decomposition number 2 talks about on page 144. Okay, and then we have number 17. Number 17 is an acid being heated, and it's breaking apart. I'm sorry to all of those people who just groaned when I said that way. I also apologize if anyone repeated me afterwards, because I know that occasionally happens. Sorry. So again, number 17 is decomposition number 4. It's got something being heated and broken apart. Yay! There we go. And let's look at the last page. 2 compounds, 2 elements, 2 pieces. 1 piece. One piece being broken apart. That must be a decomposition. And it looks like decomposition number 6? No, that's wrong. That's wrong. Decomposition number 6 says electricity. I think this is decomposition number 5. I don't have my sheet with me, so I'm hoping that I'm not wrong here. Well, look at that 5. Let's just get the actual pen. Erase this. There we go. And then I think this is a decomposition number 5. I hope I'm not wrong. I've been wrong so many times, it wouldn't surprise me if I was wrong this time. But I don't have my decomposition sheet with me, so I can't look at it. But it feels like a decomposition number 5 to me. And then the last one is a decomposition also. It is an acid being broken apart. This is actually the reaction for carbonated water. When you open a carbonated beverage, you hear that whoots, and that's because this compound, which is usually called carbonated water, its actual name is carbonic acid. Carbonic acid immediately breaks down and makes these two things, and that is this whoots, as the carbon dioxide squeezes out from the cap and then continues to bubble as the reaction continues to occur slowly in the solution, aka soda, and eventually it goes flat because all of this carbonic acid keeps going that way and the carbon dioxide disappears and it no longer has that acid in there, and so then people say it tastes flat because it doesn't have acid in it. Alright, so we just did decomposition. Yay! Now let's do synthesis. So synthesis is when two things come together to make one thing, and I see two examples right here. I have two pieces coming together to make one piece. That is synthesis number 4. Two pieces coming together, one piece. That's synthesis number 3. The big diff there is that this is an acid being made, and it's got a non-metal oxide and water reacting to form an acid. So that's the description for synthesis number 3. And when I say synthesis number 3, I'm flipping backwards to page 143 to find the different synthesis possibilities. Looking for another synthesis. Number 14. Number 14 is a synthesis problem. Oh, it's just two elements combining together, so it's synthesis number 1. And then 21 is already synthesis number 1. Don't know why I didn't hide that one. And we're good. We're good. We're good. We've done all of the synthesis. So now we got to pick another type of reaction. I don't know if you're a double replacement person or a single replacement person, but I think combustion are the next easiest, because combustion always have carbon and hydrogen and oxygen. And then I'm going to look for that whole limited excess thing. If it's excess oxygen, I'm going to write CO2. So as I go through these, choo, no carbon, hydrogen, and oxygen. No carbon, hydrogen, oxygen. No carbon, hydrogen, oxygen. Oh, next page. No, 13. Look at that. I've got carbon, hydrogen reacting with oxygen. Beautiful. So this is, and it says excess oxygen. So there's a lot of oxygen, so it's going to burn really well. So this is going to be complete combustion. It's going to completely burn up. Burn. So since it's going to completely burn up, we're going to make water and carbon dioxide. And I'm going to go ahead and reveal my balanced coefficients as well. The states of matter are very easy on this one. You're burning stuff, so it's all gases. All right. So yeah, the carbon dioxide and the H2O would both be gases because it's so hot. I do occasionally have people say H2O is a liquid, and they're wrong because it is a fire. Fires don't make liquids, they make gases, and you can see the gas floating away when you burn stuff. Mr. Murphy, these are the ones I don't really like to balance. Yeah, a lot of people don't like balancing these, so my suggestion for you people that don't like balancing them is start here. Combustion reactions can be easy to balance if you multiply the CH by 2. By multiplying that by 2, you won't end up with that silly 1/2 thing that ends up happening. Yeah, this one initially ends up with like 6.5 right here, and then you have to double everything to get rid of the 6.5. So go ahead and double the CH right at the beginning when you're starting to balance it. Alright, let's go find the other combustion reactions. Not combustion, not combustion, not combustion, not combustion, not combustion. Alright, not. Yay, combustion reaction. We have a CH plus O2. It would also be okay if it was O2 plus CH. Like the order could switch. That would be okay. Both of them are hitting together. They're not actually this one occurred and then that one occurred. They're all moving around and hitting each other. They just have to be on the left side together. Same thing's true with the products. The products are both being made simultaneously, so you could write them in either order. You could put the water first or the water second. So this combustion reaction says that there is a limited supply of oxygen. So that means we're not going to burn very well. We're going to have incomplete combustion. And so if the combustion is incomplete, we're going to make carbon monoxide and water. And then, of course, we have to balance it. This reaction's also very hot, so gas and gas. That was the last of the combustion reactions. And we're doing pretty well now. So these two, we're just identifying them, looking at the sheet. This one, it's either carbon dioxide or carbon monoxide and water. And now we get to the double replacement and the single replacement. And I want to remind you, like I said earlier, you only use the activity series for the single replacement. So let's go ahead and do that since I just mentioned it. We're looking for a single element in BC. We're not looking for two compounds. Now, at this point in the worksheet, I've only got two types of equations left. So I'm either going to be thinking this is single replacement or this is double replacement. And I'm going to go ahead and label all of the remaining ones as I go through. So if I see a single element, I'm going to label it as a single replacement. If I see two compounds, I'm going to label it as a double replacement. Okay, so in number 6, I have a compound and a single element. All the single elements. This is a... Oh, wait a minute. We're going to set that one aside for a second. That'll be a spoiler alert. But this one looks like a single replacement, doesn't it? All right? So right now, I am thinking single replacement. This is what I'm thinking about this one. I'm going to actually throw that out in a couple minutes. I'll get to you on that in a second. Number 8, single element compound. Looks like a single replacement to me. Number 11, single element compound. Looks like a single replacement to me. Number 15, single element compound. Looks like a single replacement to me. Number 18, same thing. We have a compound and a single element. Looks like a single replacement to me. Oops. Operator error. And number 19, I have a compound and a compound. That must be a double replacement then, right? Let's pick the red box. No. Let's pick the red box. Red box. There we go. Red box, not like the place where you return videos, but anyway. Number 20, oops. Number 20, compound and compound, double replacement. Number 24, compound and element, single replacement. Okay, and that's the last of them. So we've identified the various reactions. Now it's time to use the activity series. So first we're going to do number 8. So in number 8, we have lead and we have silver. And I look at the activity series and I say to myself, hey self, who's higher on the list? And we talked about that just a minute ago. We look to see if the element that's by itself is higher. And if the element that's by itself is higher, it will replace the other element that's on the list. So lead and silver are on the same list. Who's higher on that metals list? Lead is. So lead takes the place of the silver in the compound. And lead usually has a positive 2 charge, so that's why I wrote down lead and then 2 acetates. And then I have to come back here and balance it. Boom, done. Hey, how did I know this state of matter? Well, I don't know about you, but when I have silver, which I don't have a lot of silver, but if I had silver in my life and it was just sitting on the table, it would be a solid because silver is a metal and most of the metals are solids. So since that's just silver, I knew it was a solid. What about this single replacement up here, number 6? Iodine is the single element. Bromine is a single element. Brief pause brought to you by choking. Choking makes the teaching more exciting. You probably didn't notice because I actually did pause. Iodine and bromine, but now you notice because I'm talking about it. That's weird. Just stop. Okay. Iodine and bromine are both on the nonmetals list, but if you look really carefully, you'll notice that iodine is below bromine. So that means no reaction is actually going to happen. Yeah, no reaction. So if there is no reaction, then behind the red box is nothing. Yeah, you don't have to do anything. You could write no reaction on there, like if it makes you uncomfortable that nothing is sitting here, you could be like, no reaction. You know, that would be totally fine with me if you wrote no reaction here. But you don't have to because it's no reaction, and I wrote in R up here. So there's nothing there, and there's nothing there. Look at all those random empty blank boxes. Again, why is it no reaction? Iodine and bromine are on the same list, but iodine is lower on the list. Elements that are lower can't replace elements that are more reactive or higher on the list. Go down to 11. Aluminum is on the metals list. Hydrogen's on the metals list. Who's higher on the list? Aluminum is higher on the list, so aluminum replaces the hydrogen. Hydrogen's now by itself, and since aluminum's a +3 and chlorine's a -1, there are 3 chlorines. When hydrogen's by itself, it follows this rule which we've talked about a couple of times. It is what we call a Brinkelhoff. If hydrogen is alone, like it is right now, it's not in a compound, it automatically doubles up. And then we have to balance the question. Okay. Hey, how do I know the state of matter here? Well, this reaction is occurring in water. See, that's aqueous right there. So this compound could be solid or could be aqueous. How could I figure out if a compound is solid or dissolved? Solid or dissolved? I'm pretty sure on the solubility rules, we decided if something would be solid or dissolved, and things that are soluble are dissolved. So since aluminum chloride is soluble, I wrote that it was aqueous. There we go, quick little note. Since it's soluble, I wrote aqueous. Alright, let's move on. We have another single replacement, number 15. Calcium is higher than hydrogen, so it would replace the hydrogen. Again, hydrogen's a Brinkelhoff, so yabba yabba yabba. Bromine and iodine. Hey, look at this. Number 6 was iodine and bromine with sodium. Now it is iodines with the sodium and bromine's coming along. Since bromine is higher than the iodine, it is going to replace it, and now the iodine is by itself. There is a typo there. I'm going to pause for a second. No, I'm just going to do it. So this typo says aqueous, and that's wrong. It should actually say solid, because when I look at the periodic table, iodine is all in black, and blacks are solids. So that should be a solid. Iodine's not a gas or aqueous. Sorry about that. I make errors too. 24 as our last single replacement. Here we go. Calcium replaces the hydrogen and bonds with the oxygen. Okay. And I think that the only questions we have left now are these 2 double replacements. Yeah. So we've whittled it down to just the double replacements. Let's look at the double replacement pattern one more time. A is going to bond with D. C is going to bond with B. When we do this, we do need to contemplate the charges of these elements, or ions, I should say. A is positive, so it's going to bond with D, which is the negative. So since A is sodium and D is phosphate, we're going to have those 2 pieces together. And then using the charges of these elements, sodium is a +1 and phosphate's a -3. That's where the formula came from at the bottom, that there's 3 sodiums. And then I erased it because it's really not supposed to show. And then the other part is the hydrogen and the hydroxide come together to form water. And then you have to balance it, you have to put a 3 in there. And then number 20, we have the lead and the sulfur is going to come together, and that's going to make PBS. And then the hydrogen and the acetate is going to come together, making HC2H3O2. PBS is insoluble. Again, I'm using the states of matter. I'm using the solubility rules for my states of matter. Since it's insoluble, it's a solid. Alrighty. I should probably reveal what's behind this red box. That should be a 3. And this reaction is also called an acid-base because you have an acid and you have hydroxide. That's a base. So those are the 5 reaction types. You definitely want to work on worksheet 3 and become amazing, because the test is going to have a lot of these left side, what goes on the right, left side, what goes on the right. You need to practice this. There's not going to be any last second cram session that makes this just stick. So practice, 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 practice. See you later and have a good day.